Okay, so for the next talk today, we'll have Shinji, and Shinji is going to be telling us about the Airy function and formal quantum gravity.
Okay, let me first thank Vishnu for organizing everything and giving me an opportunity to give a talk. So this talk is based on work in collaboration with Pavel Zavda, who is a postdoc at the Yukawa Institute for Theoretical Physics. And I gave the same talk, and actually Robert was in the audience, and he will get bored, but you are the chair, and so you have to tell it. Okay, so now this is very simple-minded and very naive. Nonetheless, the result is kind of remarkable. And so I have Airy function and quantum gravity in the title. And so here's my motivation. So the quantum gravity part. This is a very, very shallow sense of quantum gravity. So first, we know that from ADS-CFT, 1 over n squared corrections, it gives you quantum gravity collections in the dual gravity. So my sense of quantum gravity is in this sense. So this, I target my talk on the 1 over n corrections and try to reproduce it from gravity. And we can do this because we have, by now, many exact results at finite n in supersymmetric quantum field theories by localization. So Alberto, he gave us a very nice talk on the localization related topics, and in my case, it's a simpler case of the application of localization. So in fact, in some cases, not only 1 over n corrections, but also e to the minus n quantum gravity non-perturbative effects are known. But it's great that we have many finite n results in supersymmetric gauge theories, but it is very hard to reproduce these predictions from gravity duals. So I focus really on the 4-dimensional gravity, which is dual to a 3-dimensional conformal field theory, and I am really focusing on ABJM theory. And I am focusing on ABJM theory living on the 3 spheres, not on any other manifold. That's my focus today. And so for ABJM theory, the partition function, as well as some BPS Wilson loops on 3 sphere, are exactly known in all orders in 1 over n, and including actually e to the minus n, non-perturbative effect. I don't talk about n equal 4 super units because in this case the partition function on S4 is rather trivial. There's not much structure there. And so my obsession with Airy function follows from the fact that the 3-sphere partition function and also 1/2 and 1/6 BPS Wilson loops of ABJM theory, they are given by Airy functions, and plus non-perturbative effects. And on the other hand, we know for a long time from 4-dimensional quantum cosmology that the wave function of the universe in the mini-superspace approximation is given by Airy function. So we wanted to use the similar strategy to get Airy function not for the positive cosmological constant, but for the negative cosmological constant, so that we can check whether this reproduces the Airy function which we got from ABJM theory. And as you know,
So for your earlier results,
right.
For the H3 partition functions?
Yes, yes. So these
this
are for
in the two. What do you do with K? What's K?
In the work, in my work with my collaborators, it was in the Tuft limit. So it's a type 2 element.
Okay.
But so Marini and Ptolov, they have a beautiful way of getting Airy function, which is valid for finite K. So they are in the M theory regime, and we are in the type 2A. But so by now, so it's known that for any K, it's Airy function. And so they extended this to Wilson loops. And as it is well known, the Airy function bridges classical and quantum regimes in the WKB approximation. I teach quantum mechanics, and I start from WKB approximation because it's the second part of quantum mechanics, and the only good thing that came out from my teaching is my obsession with the Airy function. Okay, so the last, and also it is known in random matrix theory that Airy function appears somewhat universally if you zoom into the edge of eigenvalue distribution, which is known as Tracy Widom. It's not that I'm an expert on this, but I found it fascinating that it appears, Airy function appears very universally, and hopefully this will be related to this Airy function of four-dimensional quantum gravity. Okay. So now, because I focus on APJM theory, so here is what actually many of you know this very well, that so in ADS4 CFT3, ADS4 is in theory on ADS4 S7 bot TK, or type 2A string theory on ADS4 plus CP3 in the top limit. And then on the other side, on the field theory side is M equal to 6, UN cross UN Chan-Simons matter theory. And it has this Tuft coupling. And the parameters of these two theories are related in this way. So the Newton's constant is related to N and lambda this way. So on this side, the gate theory side, as I mentioned, there are a lot of works on the exact result by using localization. So it started with Kapstein, Muret, Yakov, and Hamahosomichi Lee. And then, so the ABJM theory, it reduces to the matrix, to a matrix model. And then, so you can analyze this matrix model. So it's basically the matrix model is just a Gaussian potential with kind of generalized Vandermonte. So it's not the standard Vandermonte, but it's generalized to hyperbolic functions. And the partition functions, PPS Wilson loops, and index, and twist index are already computed. So there are many examples of exact result in this theory. But on the other hand, in the gravity side, large N, there's a spectacular matching between this theory and this theory that was done by Marino.
What do you mean by Gaussian? Because I understand this is an interactive matrix model, or maybe what you call this hyperbolic Vandermontes, where you find interactions.
Once you localize this on the localization locus, then the Chan-Simons part becomes just Gaussian. This auxiliary field is sigma squared.
Yeah, but then the one loop correction gives you like some interaction.
Yes, that's the Vandermonte.
Okay,
that's the Vandermonte. Yes. Okay. So now, in the gravity side, the classical computation has been done, and it was confirmed by this localization computation. And beyond large N, for this S3 partition function, there is computation by the Volker, Drucker, and Gomez using four-dimensional gauge supergravity. and they actually reproduced Airy function. So there is already a work. But today, then what I'm gonna do is the following. So as I mentioned, there's a supergravity localization computation confirming the Airy function. But today I take really the dumbest and the simplest approach and wish to make the point that Airy function appears in four-dimensional gravity even without all the sophistications of supergravity and extra dimensions. So so by this, I mean that the theory I consider is just a pure Einstein gravity with negative cosmological constant. And for the Wilson loop, I add a probe named Goto string, but that's it. So I have no supersymmetry at all. So it's the simplest setting to check the result of ABJM. So in fact, what we're going to find is that the three-sphere partition function in the mini-super approximation of pure Einstein gravity actually reproduces the Airy function, which is exactly the same one as the ABJM Airy function. And by adding Goto string, we could also reproduce 1/2 PPS Wilson loop result. So these are the main goals. And so I'm now going into more details. So this is the result known in ABJM theory. So this is three-sphere partition function. And I just focus on the Airy function part. There's some other factors, but I ignore this. And also there are non-perturbative corrections corresponding to in the type 2 limit. This is a Walsh's instanton, and this is the D2 brane instanton. And in M theory, both are M2 brane instantons. But this is the result we know. So we have specific dependence, so it's Airy function, and we have specific dependence on n and lambda, and we have these things. So there's this shift. This corresponds to higher curvature corrections, and so today I ignore this part. So I want to reproduce this from pure gravity. And so expanding this Airy function, we have this asymptotic expansion. And so this exponential part is, of course, the result, which is the classical gravity, which agrees with the classical gravity. And then there's this one loop part, which was also reproduced by these people in honest supergravity calculation. And then, given Airy function, we actually know what should be the 2 loops and 3 loops and higher loops quantum gravity collections to the three-sphere partition function. So in fact, if you count, so if you look into this parameter, then you see that this is really the Newton constant expansion. Okay, so but today, so I want to just reproduce this thing. Well, actually, I reproduce this thing. Okay, so here is what I do. So it's, as I said, so this is Einstein-Hilbert action plus Gibbons-Hawking-York term. It's a Euclidean Einstein gravity. And I set the boundary condition to be three-sphere. And I just want to do this path integrals. That's all what I want to do. So this action, so Einstein-Hilbert part, including cosmological constant and the Gibbons-Hawking York term. So of course it's not easy to carry out, and of the UV divergences, and you cannot do this usually. But what we're gonna do is a drastic approximation, and we do not have good justification, but the only justification is the final answer, which agrees with ABJM. So the approximation we do is, so first, this is the ADM type parameterization of metric. So you have lapse, and you have a spatial metric, and you have shift. So mini superspace approximation in this context is we set shifts to be 0, and the lapse and the spatial metric depends only on this radial coordinate. In the quantum cosmology context, what people do is, so instead of radius dependence, they only keep the time dependence, and they ignore all the spatial dependence.
So does this mean you're integrating over all metrics that preserve the SO3?
Yes, that's right. And of course, there's no guarantee that this will give you the right answer. But in the end, you will find that it does. So in this ADM parameterization, our action becomes this. So this is Einstein-Hilbert plus a Gibbons-Hawking York. So you have scale factor dependence and lapse dependence. And here, so it seems so this. So now we're gonna make a simple change of variables, but this seems to be crucial. So this is what people do in the Dosita case. And
so when you write that, these measures are just naive measures?
yes, very naive. I am, so on purpose I'm agnostic about this. I will not, but I will justify it later. Yes.
How do you know what the correct answer is and why comparison to ABJ is the correct thing? This is just pure gravity, right?
Yes, pure gravity. Yes, so our story would be if we add all the supersymmetries, many cancellation happens, and then introduced to this mini superspace. But that, of course, that's a naive expectation. It's not super rational. So yes, it's more like wishful thinking. So this is crucial. And so what people do in quantum cosmology is they rescale the lapse this way, and then they set the gauge in which the lapse is constant. And then, so then this action becomes this, and now we introduced Q, which is the scale factor squared for our convenience. So this is the action for which we want to do the path integral. And so even this one, we are not going to do the whole path integrals. We will make another approximation. So which is okay, sorry. So what we're going to do is, so given this action, and then we will perform this path integral in the saddle point approximation. So n is constant, and we first want to do the Q integral, and we do this by saddle point approximation.
So when you say fixing nr equals constant, this is the r goes to a function of our coordinate transformation that does it?
Yes, that's true. So you can do the change of coordinate to make it, what we mean by this is with this rescaling, we really fix, so there's going to be an n over a squared, and then we just n to be constant. I guess it's equivalent to some change of coordinate, but we choose particular coordinates for this.
Okay.
Yes.
What are you doing for the measure of this? Because you're
interested
one corrections, right?
Yes,
so then the measure
so we will be very unclear about this. But later we will justify this from other viewpoint.
But you agree that it matters for the one for the loop
yes,
correction.
I absolutely agree with you.
Not for the side.
Yes, I agree with you. So, but let's see. In the meantime, So after we do the calculation, we claim which measure is the right one. Okay, so now it's actually quite simple. So this is kinetic term because n is now constant. And then there's a linear potential. So you almost see a Airy function because the Airy function is a solution to the linear potential problem. Okay, so but you have to get the right Airy function. So by performing this Q integral in the saddle point approximation, this is what we get. So because this is asymptotically ADS space, we will have these divergences. So this is the standard, the usual UV divergence we have in this type of calculations. And then we have finite part. So this Q naught is one parameter which characterizes the saddle points of this action. This action. So I will mention what the saddle point is shortly. So, but the final answer depends on the cutoff Q infinity and some one parameter Q naught. And by the standard holographic renormalization, these can be precisely cancelled. So this is really the standard holographic renormalization procedure, and you can easily check that these are removed by these counterparts. So we will be left with this finite one. Okay, so now I mentioned what the saddle point geometries are. So this is the saddle point solution. It's super simple because it's just a linear potential action. And this is our saddle point geometry. And so it looks like this. So for generic value of this one parameter Q naught, it's conical. But there's a special value of Q naught in which this geometry becomes smooth. And this is actually ADS. And also, as it turns out, so this is the saddle point of the saddle point. So what we're going to do is, so we get this, and then now we integrate Q naught. And then, so with this action, the saddle point is Q naught equal to L squared. This is ADS. But otherwise, it's conical. And so these geometries does not satisfy Hamiltonian constraint. So it's offset. But it has to be offset because if we want to get any quantum corrections, it cannot be just on-shell. And in fact, this is very similar to, so conceptually, this is very similar to the game theory localization or superconducting localization in that the lossy of path integral is offset. And I should mention because this at the tip of this cone, we actually have scalar curvature singularity, but the action is finite, first of all. And second, we have to deform the contour of this Q naught integral. And when we do this, actually we avoid all the singularities altogether. But this choice of contour is to reproduce the Airy function that we want to get. Okay. So this is what we have, and so we want to perform this Q naught integral, and then expanding Q around this saddle point, we have the fluctuation for Q, and also we have lapse.
So the statement is if you have done the gauge fixing correctly, then you don't have to do this. And the classical symmetry that arises always satisfies the Hamiltonian constraint, right? Because anything that's gauge invariant has to satisfy that.
No, but in the path integral, you have to go offshell.
Sorry?
In the path integral, you always
I know,
go.
but you're looking for a classical solution.
Yeah. Okay. So yes.
And then the classical solution better satisfies.
Yes.
Constraint.
So to be.
So can you think of this Q naught, this integral of Q naught as enforcing the Hamiltonian constraint?
No, so not really. So if you take into account the lapse equation, of course we go back to onset, but we don't actually do we don't consider the saddle point of lapse equation. So that's because the Hamiltonian constraint is the equation with respect to the lapse, but we make it loose.
I see.
So yes, because it was actually a two-variable problem. Yes, lapse. Sorry. Yes, lapse and Q. And what we did is we only considered Q equations of motion.
I know, but there are momentum constraints and there are Hamiltonian constraints.
Yes,
right?
momentum constraint, we actually set the shift to be 0, and so it does not appear here. It's approximation. Yes, but we don't impose this constraint from lapse equation.
But you continue to do the path integral over N?
Yes, but in the end, it does not matter. That's our argument. So this is what we got, and then there will be this fluctuation integral, and moreover, we will have lapse integral. But we claim that none of these integrals of the lapse and fluctuation do not matter. Because it will give you a simple dependence on the lapse, and it does not give you any non-trivial factors to the partition function. Okay, so now having this, we make the change of variables like this, and we identify the Newton's constant with the gauge theory parameters. And then this is the final answer we get. So because it's already in the form of Airy integral. So now, so here, of course, I put this parenthesis because we are unclear about the choice of measure. But we claim that this is the choice. So with this parameterization, Q naught to A naught squared, so this is the measure we have to take. And this is indeed the Airy function you find in the ABJM theory. And even we know the meaning of this A naught in gauge theory. So this is done by Marino and Ptonov. So they use some Fermi-Gas representation of the matrix integral. And this A naught corresponds to the chemical potential of the grand partition function of this ABJM matrix.
So sorry, so if you're integrating over A naught, it is imposing a constraint. If you just
I'm not, I claim as the lapse integral is...
No, I'm saying that you just gave us this interpretation that A naught is a chemical potential.
Right.
And you're integrating over it.
Yes, we are integrating over
a
it.
chemical potential, that's just imposing a constraint. That's what it means to have a constraint, right? You take some gauge potential, you integrate over it, and what that does is imposes a constraint.
Yes, but it's not the Hamiltonian constraint.
Okay, we can, yeah, that might be the case, but it is, there's some sort of gauge freedom that you have in your theory that you have to fix, right? That's what this line is saying.
No, this line is,
No?
it's more a trick. No, it's not like that, no.
Well, maybe you can tell us a bit about that calculation for the Fermi-Gas, but if you have a chemical potential that you integrate over, what that means is that
Yes,
you're imposing a constraint, right? Like projecting zero charge sector.
Yeah, right, okay, but right, but my point is that constraint, I don't know what, but it's not this Hamiltonian constraint.
Okay.
So, but this way, we produced Airy function, and so here we have to choose the contour so that we get the AI instead of BI. And then we have to complexify this metric. So, but that way we are actually avoiding this conical singularity.
But you're going to complex geometries.
Yes, but yeah, it is. I don't know the physical meaning, of course, but yeah, but because we want, this is the one we want to actually produce, and it seems that the discharge is.
So let me try to understand. You integrate it over
This,
N.
so this, the lapse, this N is gauge theory N.
Oh, okay.
This
So
N is
that's
the
what
lapse
we were
N.
confused. That's the
Maybe
lapse
that's
part.
maybe that's the.
Okay.
Sorry, so this N is actually lapse. It has nothing to do with length of the gauge group.
Got it.
Sorry.
Yes.
Sorry. Yeah. So this simple-minded, naive approximation gives us the answer we need. So of course we don't know why it works.
How would you distinguish, let's say, if you want to do a supersymmetric versus a non-supersymmetric path integral?
How do you distinguish?
Yeah, so for your case, we are just doing something. How would you know that this is supposed to represent the result of a field theory supersymmetric computation or a non-supersymmetric computation?
Well, we believe, so the way we want to think of this is we are reproducing the supersymmetric, the result of the supersymmetric case. And if you do it right, so if you do choose particular way of localization in supergravity, maybe in the localization locus, it reproduces this one. It reduces to this one. That's what we want. We wish. So I must say, so it's all naive, of course. Yes. The final answer is the agreement with ABJM. Well, it's not completely logical, but it sounds nice, and that's the only thing that we rely on to justify whatever we do.
When Daboyka and collaborators got the same function, did they get the same integral representation but with some other variable, or a different integral representation?
Right. So it's the variables are completely different. So because for them, the gravity sector does not matter.
Right.
So it's the only scalars in the vector multiple.
Yes.
But they get the same integral over that.
Yes. By doing some, yes. In the end, yes. Right. And well, so it could have been a coincidence, but we can go a bit further. So that's why we want to calculate something else than partition function, and as an example, it's half BPS Poisson loops in ABGM theory. So the half BPS Poisson loops, which corresponds to the winding strings, has this answer. So it's again Airy function, but the argument is shifted by this much, which is proportional to the winding of the string. And so because we ignore this, well, because it's a higher curvature collection, and so we cannot reproduce it, so we want to reproduce this shift from pure Einstein gravity plus Nambu-Goto string computation. So what we're going to do is just adding a probe string, and then we need to find a minimal surface anchored at this great circle of sphere, which corresponds to this Poisson. And we do this not in the ADS geometry, but in the saddle point geometry we found. And the minimal surface is actually trivial. So it's just a two-dimensional subspace of our saddle point geometry. And in the classical limit, or in the ADS limit, this is ADS2, and which agrees with what we know. And so now, given this minimal surface, we calculate the on-shell Nambu-Goto action in the off-shell geometry. And this is what we get. And so this is a divergent part, and this is a finite part. And what is important is this coefficient, but this comes out right. So as we translate all this result into the gauge theory language, then it precisely reproduces this shift, what people found in the ABJM theory. So this is somehow working, but again, I don't know why this is working exactly. So it's important to know that why this is actually working. Yes.
I'm confused. Why are you able to reproduce the 1/2 BPS with some? Because as you mentioned, there is also the 1/6 BPS.
Yes.
And the difference between them essentially is the boundary conditions for the directions in the compact space. But
Right.
here you are just using ADS4, so you are not saying anything about
Right.
the CP3.
Yes, yes,
And then
that's
so
right.
you are obliterating all this,
Yes.
and then you get the result for the 1/2 BPS with a loop that precisely knows, what are the boundary conditions in the CP3. So,
Right.
or how would you get the 1/6 and
Okay,
I understand the question.
yes. So for the 1/6 case, actually, it wasn't clear when I checked the literature. It wasn't clear what is exactly the dual, because in the original paper by Nadav and company.
They talk about an screen, but you can think of it instead of the 1/2 BPS.
Yes.
It's like it's near the point of the 3, so
Yes.
you have division boundary conditions
Yeah.
for all the directions in the
Okay.
space. But this smoothing they talk about can be seen as some of the directions,
Yes.
some of the coordinates on the CP3 instead of Dirichlet satisfies normal model.
I see.
So from the string point of view, that's it. That's the difference. So.
I see.
But since you are not taking into account the compact space, the CP3,
Yeah.
so
Yeah.
how would you see that?
I guess the 1/2 BPS case, the internal space CP3 doesn't really matter not much.
Right.
But that could be the only reason why we can reproduce this. So from our viewpoint,
No, it's clear you reproduce that. It's just I would like to understand
Okay.
how it is that you reproduce without knowing the
yes,
details.
another reason for us was more technical. So 1/2 BPS case, it's a beautiful Airy function. But the 1/6 BPS Wilson loop case, you have a combination of some Airy functions. So that simple result for 1/2 BPS, we thought, so this is the only thing we have to explain, and so we thought we can do it. But of course, the information of the internal space is all condensed in this identification of parameters. And if anything non-trivial happens in the internal space, we cannot reproduce the result. I agree. But that's why maybe 1/6, maybe it should not work. But 1/2, it somehow works. So we produced two of them, and what time do I?
You still have 20 minutes.
20 minutes, okay. So now, so many approximations, mini superspace and saddle point approximation, and we choose the measure we want. So we are really hand waving, but for the measure part, this might give us one justification. So because so now we want to consider the Wheeler-DeWitt equation in this approximation. So then this is the Hamiltonian constraint. So our Hamiltonian is the linear potential. So this is the Schrödinger equation we want to solve. And of course the answer is the Airy function. And so then we want to ask, so how this wave function is related to the partition function on 3-sphere. And the answer is actually that, so the wave function depends on Q. And on the other hand, the partition function has no dependence on Q. And the answer to the question how they are related is the following. So the 3-sphere partition function corresponds to the wave function at Q equal to 0. Because, well, you can see it explicitly. So because this is the solution to this equation. And then if we set Q equal to 0, and if we impose the boundary condition such that it doesn't blow up, then we ignore Bi. And then this with q equals 0 is precisely the Airy function we got for the three-sphere partition function. Okay, so that gives us some consistency check.
So it was 0 the value in which it reduces to ADS?
Yes, not the ADS, but the partition function. So I'm gonna introduce Q now.
Okay.
So then how can you actually get this wave function with Q dependence? This is how it works. So in this path integral approach, so this is the thing we actually calculated for the action of the saddle point. And then we did the calculation. So the lower limit of this integration was set to be 0. So that corresponds to integrating over integrating for the entire space. So from q equal to 0 to some cut of q infinity. That's what we have done. Then if we cut off the geometry at some finite q, we have q in the lower limit of this integration. And so if we do so, then this partition function with this infrared cutoff dependence is precisely this wave function you get from the Fourier-Duet equation. So you kind of expect, because Q is corresponds to the scale of the conformal field theory. And so the wave function with finite Q corresponds to the partition function in which the momentum modes are integrated only partially, not completely, down to the infrared cutoff. So, in fact, in 2000, a long time ago, so Dubois and Ferrinde, they suggested that the conformal field theory partition function is a solution to the Fourier-Duet equation, and this is in a way a concrete realization of their idea. And also, if you look at the naive free energy defined by this minus log partition function with cutoff, then you see that this monotonically decreases as you go to the infrared, because the Airy function for large argument, it's a monotonic. So this is kind of reminiscent of the FPLM for the odd-dimensional conformal field theory. So, but our point is that I'm
sorry, I'm getting confused about it. Yes. There's the radial coordinate,
yes,
and there's Q.
Yes.
These are two separate things, right?
Yes, but so the saddle point relates them.
So what was Q again, please? Q
Yes.
was a function?
Yes, Q was a function.
Basically?
So so this was the metric. And it is related to.
So stopping at some value of Q is basically stopping at some value of the radius.
Right.
And then there was another parameter which characterized which saddle point solution you were at.
Yes.
What
so
was that parameter called?
Q naught. Yes, Q naught.
So you're fixing Q naught and looking at things as a function of Q.
Right.
Is this right?
Yes. Oh, yes. Okay.
For any given Q naught, you're looking.
Right.
So you're thinking of the evolution of the wave function as being the initial conditions at the boundary, and then you're going into the boundary.
Yes.
Is that right?
Yes, that's right.
Thank you. And the wave function,
Yes.
you should think of as at some fixed Q.
Yes.
Does Q naught also fluctuate? Is the wave function a function of Q and Q naught? Is Q naught
Q naught
is frozen because
Q naught we integrate.
but right.
Yes.
I see. I mean, a fluctuation from one Q naught to the other.
Right.
Is that infinite action? So it cannot be part of the same wave functions.
The integration from Q naught to.
So you have these many different saddle points.
Right.
I want to know whether for every saddle point there's one wave function, or there's a wave function that also includes amplitude for saddle points, or it's an ill-defined question.
So from the path integral viewpoint, Q naught, it's a part of the integral. So we really have to integrate.
So that means it's part of the wave function?
Yes, that.
So the wave function is a function of both of time as well as some parameter?
The wave function is just a function of Q corresponding to this infinite curve.
At some fixed Q.
Fixed. Well, no, it's actually Q naught is
You're going to
already
sum
integrated.
over all satis.
Yes,
to get
we do.
this answer.
Yes.
Maybe-
So you don't get a dependence on Q naught.
Right. Right. That's right.
Maybe the confusing thing is that when we typically think about the wave function of the universe,
Yes.
the parameters it depends on are sources at the boundary.
Right.
So you think of having the IR state fixed,
Yes.
and then you're computing the overlap
Right.
of whatever it is that you constructed, of
Right.
your state in the IR, with some out state, which
Right.
is the,
Right.
the UV sources.
Right.
Here you're doing something a bit, it looks the opposite, right? You're fixing the UV out state, and it's like you're changing the IR state.
That's right. Okay.
But
yes.
that's not how we think about, right? So you generate one state, which is the vacuum, and then you ask what is the transition amplitude
Mhm.
to whatever universe of
Right.
observe
Right.
at the
Yeah.
boundary.
Yeah.
So in that sense, it's a bit unclear what you're supposed to integrate over, right? Because
Okay.
it's like you're fixing the outcome of the experiment,
Yeah.
and you're integrating over states.
But okay. So in quantum cosmology, so it's the scale factor, and then you
No, but
fix.
the scale factor is defined at infinity. That's exactly, the scale factor in cosmology is one example of that, and it's exactly the size of the metric
Yes.
at infinity.
Okay.
So it's a
Right.
UV source, it's not something that lives inside. That's a good example. So that's a case where what you do is you fix something at the boundary. The inside is fixed, you don't touch the inside.
Right. So.
So if you're going to integrate over Q to compute
Right.
probability, it's a bit strange, right?
Okay. Yes, but okay. Let me see. So to be precise, this is a function of Q and Q infinity. So this is an evolution from Q infinity to Q in the radial time.
I know, but
Yes.
but that's the IR state.
It's the IR state. Yes.
Yes. Okay, but that's what's confusing.
Okay.
The natural thing would have been, so in that formula that you show us with the Airy
Yes.
functions and the other piece,
Yes.
would have been to change the boundary conditions in the UV,
Yeah.
and then to define the wave function in terms of those.
Right.
Right, because you want to
Yeah.
integrate over Q, right?
Yes, I reintegrate over Q.
So,
We integrate over Q in some range. So we have to specify the limits of Q integral. So that's what we have done. And Q naught is something else. We really have to integrate. Okay, I'm not very clear about the interpretation, but by wave function, what we mean is really just a solution to the Hamiltonian constraint.
but in terms of a path integral formulation, what it should be is something that depends on sources at infinity. Like you said, like the scale factor.
Yeah. I don't have really clear response to your question at the moment. So let me think about this. So I think how much time?
You have 10 minutes.
10 minutes. Yeah. Okay. I skipped this docit thing. So yes, I will be finishing soon.
Sorry, but you didn't justify the measure. Did you do that?
So the justification of measure is the agreement with this wave function. Yes. So right, yeah, that's the only thing. Yeah. Right. So now, lots of questions I cannot answer. Sorry. But we can go on to calculate something else and to see to what extent this really works. And for example, we can compute a two-point function of heavy operators. But because in that case, we can approximate two-point function by a geodesic. So we just calculate geodesic in this saddle point geometry. So then this is the answer we get. But the problem is that we don't know. As far as I know, there is no result in ABJM theory for this two-point function, and so we don't have anything to compare with. But this is what we get if you just calculate. That's one thing. And so now, also, the Wilson loop in this case, in dimensions, it coincides with the holographic entanglement entropy. So we can actually kind of calculate the holographic entanglement entropy by using a Liu Takayanagi prescription to compute the minimal surface anchored on this circle. And this is the same as the Wilson loop calculation. And if we do this naively, this is the answer we get. So this is the part which gives you the classical area of the minimal surface. But this cannot be the correct answer because we know that in three-dimensional conformal field theory, this entanglement entropy has to be minus free energy. So we are missing something, and I have to resolve this issue. But once we understand this,
This is the entanglement entropy of what region?
so on the S3,
Half of it, or
yeah, it's kind of half of it. It's the equator of S2 inside S3. And yeah, if we can get it right, then we hope that maybe we can learn something about quantum gravity collections to Liu Takayanagi, which was discussed by these people. That's the other observables. And other dimensions, well, it does not work. Like in the S5 case, clearly it doesn't work. So in the odd dimensional LDS or even dimensional conformal field theory, you have conformal anomalies, and we believe that this anomaly will give you some ambiguity of the choice of cutoff, and that's the reason why this method does not work for odd dimensional LDS case. So it has nothing to do with it has nothing to do with mini superspace approximation. But it just doesn't work. Okay, but however, we want to note that if we nonetheless calculate the wave function of the wave function or the four-sphere partition function in this way, then it is a Hermite polynomial, which kind of is reminiscent of Hermitian matrix model you get for N equal 4 square this. But we don't see clear connection between them. But so for the even dimensional ADS, in other dimensions it might work, and so it's worth looking into ADS 6 case. By now we have gauge theory answer and the classical gravity answer, and so we can actually test beyond a large n. So as I have already mentioned, the relation to this supergravity localization, well, it's not entirely clear. So as my answer to Shiratsu, they are very different. So in our case, it was a scale factor. But in their case, it was the scalars in the vector multiplet of supergravity, which is the parameter of the Airy integral. So the relation is not clear, but because localization is not unique, so there are many ways to do the localization, and so maybe there is a way there's a way of supergravity localization which gives you this mini superspace, which reduces to the mini superspace. And well, other things you can calculate, so that's future directions. But finally, But this is the thing I'm most interested. Actually, it's related to Alberto Zaffaroni's work. So we want to apply this to ADS4, magnetic black holes. So in that case, we have to change the boundary condition from 3 sphere to S2 plus S1. I have gone to some. I have got to some point, but I'm a bit stuck. Anyway, so for this, as Alberto talked about, so for the ADS4 black holes with magnetic charges, there's a spectacular agreement at large N. And so it's natural to wonder whether this approach can be used. And yeah, so the boundary condition is S1 plus S2, and also we have to add the scalars and U1 gauge fields, and it's easy to set up the problem and easy to reproduce the classical result, but I haven't figured out how I can really get 1 over n from this, so not yet. And okay, finally, maybe in this approach we have a bunch of saddle point geometries, and which seems to be the one dominant one contributing to the partition function. So in a way, that's a microstate geometries parameterized by this Q norm. And in the black hole case, maybe this microstate analogy becomes sharper because there will be some saddle points which are the dominant one contributing to the black hole entropy, and then it might be really sort of a microstate geometry. So that's why I'm very interested in this application.
But now you are not considering any more pure lines and...
No, it's not. So yeah, so you have 3 scalars and 4 U1 gauge fields. That's very complicated,
yes.
But in the simplest case, you have all charge same with some constraint. That case, I have 1 scalar and 2 U1s, and in that case, I can go pretty far. Yes, so that's what I have done so far.
But you take still a non-supersymmetric theory, right?
It's non-supersymmetric theory, but only the bosonic part. Only the bosonic part of your case. Yes. Okay, so that's the thing. And okay, so thank you for your attention.
So we had a number of questions, but we still have a few minutes if anybody would like to ask another question. Okay, I think let's thank Shinji for a very entertaining talk.